We are now ready for problem 8 on this test review. And problem 8 and 9, we're given two functions or two equations, and the question is use derivatives to find the intervals of increase and decrease. So although we've talked about this in class, let me just take a quick minute to sort of briefly go over and summarize what it is we're talking about. I've just made up a pretty simple graph here of a function, and here's the question for this graph. I want to know where is the graph, or where is the function increasing, and where is it decreasing. So maybe I'll just make up some numbers. Say I'll call that -3. I'll call this -1. So a function or graph increasing means when you go from left to right as you're tracing the graph, if it's going up, it's increasing. So as this graph starts out, and once again, if you want to, you can think of way out here as negative infinity. But anyways, as I'm moving to the right, increasing, it continues to go up until finally it reaches like this maximum here. So the graph is increasing until right here, and then it levels off for just an instant, and then it begins to go down. So as I continue to go here, all of a sudden it's decreasing. So my graph is going down until I get, once again, sort of bottoms out here at this is like a minimum. And just for an instant, it's flat, but then what happens is it begins to go back up again, and that becomes a region where it's increasing. So you can see how, as it turns out, if we're looking at where is the graph increasing or decreasing, or where is it going up and going down, there are really sort of like three regions. And these regions are defined by when does the increase and decrease change. So for this one, if I just wanted to say where is it increasing, I could give an interval. Increasing's here. It starts at negative infinity, and it increases until I get to where x is -3. So that's this whole region increasing. There's also another region where it increases that starts at -1, and this time it goes to infinity. So these two are my increasing regions. I do have a region where the graph is decreasing, and it starts at -3 and decreases until it gets to -1. So graphically, pretty easy to see. Now let's talk about what this means in terms of increasing and decreasing. Another way you can think about it, increasing regions is where we have a positive slope. So there the slope is positive, here the slope is positive, and the decreasing, that's where the slope is negative. Now if we think about mathematically in calculus, the slope is really the first derivative. So you could say this increasing region is where the first derivative is positive. The decreasing is where the first derivative is negative. And once again, if we're back to increasing, that's where the first derivative is positive. Because the first derivative is actually the slope of the line. Interesting thing is, what happens at the maximum and the minimum? in this case, the maximum and the minimum we call critical points. Now for this example, you know what happens at the max and the min? The graph flattens out, which means it's not increasing nor decreasing, it's just flat, which means the slope, if we would draw the tangent line at those points, it's horizontal, which means the slope is 0. That's another way of saying the first derivative is 0. And these actually are the points that break up our graph into regions. So here's the idea. Say you're not given a graph. Say you're given an equation, and you're asked where for this equation is the graph increasing or decreasing. What you want to do is, if you can find these critical points, then you've broken up the equation into regions, and then if you can go into each region and figure out whether it's an increasing or decreasing region, then you've answered the question. And that's what we're going to do in a minute. But let me give you a couple other kinds of functions that we can have, just so you'll be aware, so you can visualize them, because we're going to do math in a minute. Say we had, so it's decreasing, it levels out, but instead of going back up, say it levels out, or just for fun, let's just say it does this. And let's say this point here is -2. This point here is 3. Same question. Where are the intervals? Where is this function increasing or decreasing? Well, here, decreasing, although when it gets to here, because this thing gets flat, at the point where this function is flat, it's not decreasing anymore. So in other words, this is decreasing. Here it's flat, although after it's flat for a while, it starts to go down again. So it continues to be decreasing until you get right to here. And then from this point on, it's increasing. So if we say, what's the interval where it decreases, we would say -infinity to -2 has to stop here, because for a little bit here, it's not decreasing, it's just flat. But then it picks up again from -2 all the way to 3. And where is it increasing? There's only one place where this is increasing, this last little tail here, 3 to infinity. Now let's think about the critical points. Once again, in this case, critical points are where the graph flattens out, which is another way of saying where the slope is 0, which also means where the first derivative is 0. So it flattens out right here. So I have a critical point when x is -2, and then down here it flattens out again, and I have a critical point when x is 3. So at the critical points, oftentimes we break our graph up into these regions, because oftentimes when the regions switch, oftentimes the increase or decrease switches, which means the first derivative switches. But in this case, this is one of those cases where we're decreasing, it flattens out, but it doesn't then go up, it then turns around and keeps going down, so it continues to decrease, although there's this one spot in here where it's actually not decreasing. Once again, at all these critical points, at both these critical points, the first derivative equals 0. So if you were given an equation and you were not given the graph, and you were asked, look at that equation and break it up into regions of increase or decrease, what you do is you go set the first derivative of the equation equal to 0, and that defines your regions. Then you can figure out what's going on. And one last quick example that we occasionally face. How about we have some kind of you have a graph like this, and you're asked to say where is the graph increasing or decreasing. When you look at it, it's this part of it's going down, it's decreasing. And then this is one of those graphs where we have a break or a jump. This is called a vertical asymptote. You have a jump and you pick up here, but as you keep moving to the right, it still is decreasing. So actually both parts of this graph are decreasing. Now you may ask yourself, well, what would the critical point be here? In the previous example, the critical points are where the graph was flat, which meant the derivative or the slope was 0. That doesn't even occur on this graph. However, there's one more source of what we call a critical point, and that's where you have like this asymptote. So if this was like at 2, you would say critical point at x equals 2. Because the critical point is really the values of x that break the graph up into regions. And we have this break here. We consider these 2 different regions. So just, I won't even do anything more with this, but just touch on, sometimes this happens where you've got these vertical asymptotes and there's breaks, and wherever these breaks are, that also breaks up into regions. All right, with that visual, now let's actually take the next step and not look at graphs, but actually look at an equation. And they're going to give us an equation or a function, and they want to know where the regions or the intervals of increase and decrease. So number 8 says f of x equals x cubed plus 3x squared plus 1. And they want to know for this function, basically where is it going up and where is it going down? Where are the intervals of increase and the intervals of decrease? Where is it increasing, where is it decreasing? Now we don't have a graph, so we can't visualize it. But what we're going to do is we're going to sort of look at the same things that we looked at on the graph, and that's where we need to find critical points, because the critical points breaks this up into regions, and then we can go in, once we know how many regions there are, we can go into each region one at a time and decide whether that's an increasing or a decreasing region. Because the key is, inside of a region, It is not going to change. Once you're in a region, if it's increasing, the whole region is increasing, or if it's a decreasing region, the whole region is decreasing. The only time it can change from increase to decrease is when you go into a new region. Now the way we figure out the regions are broken up by what we've been calling those critical points. And usually there's two sources of critical points. Just say it again here. When the first derivative is 0, that's the case where the slope is equal to 0, which means that tangent line is horizontal. We've seen that before. This occurs when there's maximum or minimum, or what we call a flat. In class, we sort of named this kind of point here a flat. It's not a max or a min, but it does get flat, and then it keeps going the same direction. The other source of critical points, which breaks up into regions, is when it's undefined, and those are almost always those vertical asymptotes. Right, this is this example down here. The vertical asymptote was x equals 2, and that breaks these up into regions. Now in this case, because I've got like a polynomial here, the only time you have those vertical asymptotes is when you have a fraction, when your equation or your function's a fraction. So I don't have that here. So the only thing I have to worry about here is I need to go find out for what values of x is my first derivative 0. And those are going to be the critical points. And once again, the critical points will break it up into regions, and then I can go into each region and see if it's increasing or decreasing. So the whole key is you take the first derivative, 3x squared plus 6x, and you set the first derivative equal to 0. So right now, we're doing this to find critical points. So I'm going to factor out a 3x. The solution for this is 0 and negative 3. See, good thing I checked. I'm sure you all saw that. Wow. Zero and negative 2. So those are the critical points. These are the points where the slope equals 0 and where you either have this or you have this. I don't know which it is, but I know that's what's going on here. So what I'm going to do is I'm going to draw a little, sort of like a graph, just a pseudo graph to help me see what's going on in the regions. So this is like my x, so minus 2 is right here, and I'll put 0 here. And these critical points break up into regions. Region 1 goes from negative infinity to negative 2. Region 2 goes from x equals negative 2 to 0. And region 3 goes from 0 to positive infinity. So as it turns out, for this equation or function, there are 3 regions. Now inside of each region, it's either going to be increasing or decreasing. I don't know which it is, but I know inside the region it cannot change. The whole region has to be the same. Now the way I like to do it is to make like a little sign chart here, pretty simple. I list this case there are 3 regions, test point, what I'm going to do is I'm going to pick a value of x in each of the regions. So for region 1, I need to choose a number between negative infinity and -2. I don't want to choose the critical point or that border point. I want to choose something like -3. Region 2, between -2 and 0, I'll choose -1. Region 3, something greater than 0, I'll choose 1. And what I'm going to do is, within each region, based upon this test point, I'm going to determine the first derivative inside that region. And I don't even care what the number is. I only care is if it's positive or negative. Because a positive slope means it's increasing, a negative slope means it's decreasing. So let me just, to make it clear, here's my equation for the first derivative of the slope. I'll write it in factored form. So -3, I plug in for x here. And I plug in -3 here. Let me just say I get a -1 times 3 times -3 is -9. This ends up being a +9. I don't really care about the number. All I know is region 1 is a positive region, which means that's a region where the function is increasing or it's going up. Region 2, you can hopefully see if I plug in -1 for x, the parenthesis ends up being a +1. But then I got a -1 out here, so negative times a positive. Region 2 ends up being a negative region. So in region 2, my function or my equation or my graph is decreasing, it's going down. Now if I go check region 3, I plug in a 1. 1 plus 2 is +3. 3 times 1 is +3. 2 positives make a positive. Now at this point I'm pretty much done, because I've now determined region 1 is an increasing region, region 2 is a decreasing region, region 3 is an increasing region. So now I can pretty much answer the question, because that was what the question was. The interval where it increases, -infinity to -2, and from 0 to infinity. The region where it decreases is from -2 to 0. So the whole key is take the first derivative, set it equal to 0, find those critical points. Those critical points, then break it up into regions, and then figure out the first derivative for each region. All right, let's do number 9 quickly. I think it's the same kind of problem. Here the function or the equation is f of x equals once again, because there's no fractions here, there's not going to be any vertical asymptotes, so my critical points are simply going to be wherever the first derivative is 0. So let's go ahead and take the first derivative. Hope I don't make any mistakes. And it might help to factor. I think I can pull out a 2x squared. 3 minus 2x. So now to find their critical points that's equal to 0, and you solve for it, and it looks like you have solution would be x equals 0 and x equals 3/2. So those are my critical points. So in this case, those are the points that are going to divide up into regions, because these are points where the first derivative can change from positive to negative, negative to positive, or it could stay the same. But the only way to know for sure what's going on is to do our little chart. Turns out I have 3 regions. So I do what's called my sign chart. 3 regions. I go inside of each region and choose a point. Region 1, I'll choose -1. Region 2, I have to be between 0 and 3/2, like 1 is in between. And for region 3, I'll choose 2. And then I'm going to go, for each of those test points, figure out the sign of the first derivative. So if I go here, first thing I notice is no matter what I plug into x squared, it's always going to be positive. So actually this out here is always positive. So the whole key is what's going on inside the parentheses. When I plug a -1 inside the parentheses, you get 3 plus 2. So region 1 is a positive region. When I plug in 1 into here, 3 minus 2 times a positive number still. I'm going to plug in 2. I get 3 minus 4. This is negative times a positive. So region 3 is negative. So what do I have here? If you think about it, if region 1's increasing, but region 2, since the slope is positive, that's also increasing, and then region 3 is decreasing. So it's like it's going up. Now we know when it gets to here, it flattens out, and then it keeps going up. And then when it gets up here, it flattens out, and then it goes down. So it must be one of those where it goes up, and it flattens out, and it continues to go up, and then finally it has like a maximum and goes down. Although actually for this problem, we don't really even need to know all of that. All they want to know are the intervals of increase and decrease. So increasing looks like -infinity to 0, and then also from 0 to 3/2. And the intervals of decrease are from 3/2 to infinity. And just to make sure I didn't mess up, let's see what the key says. And I believe that's correct. All right, so that's one of the first things we did once we started applying the first derivatives to these functional equations. And next what we're going to do is we're going to do the same kind of thing, except we're going to figure out if we have a max or a min or a flat at these critical points. But I'll go and stop this video now, and we'll pick up with problem number 10.